think we should be live now.
All right. Welcome, everybody, to this talk on anticipating critical transitions in psychological systems using early warning signals, theoretical and practical considerations. And that's quite a mouthful, and I have a lot of stuff prepared. So I hope to keep it exciting, sort of engaging and interesting. But if this is your first contact with sort of concepts in dynamical systems theory, it might be occasionally quite steep. So just let me know in the Zoom chat when something's unclear, and I try to if you have any questions, I try to tackle them in real time. Note also, I mean, this is going to be recorded. The slides are going to be made available. There's lots of further references scattered throughout the slides that you can read in your own time if you're interested. So yeah, I mean, I talked during a lab meeting before, and if I'm given an hour, I'll talk an hour, and so I just tried this talk earlier today, and it took an hour. So of course, feel free to leave at any time, if you can't stay the whole duration. Okay, let's dive in. So this talk is based on a preprint we recently preprinted with Anton Pichler, Arta Chica, and Andrea Baccineri. And I met those folks during the Santa Fe Institute's Complex Systems Summer School, which was really a profound educational and social experience. And I recommend it to anybody who's interested in complex system science. And I don't think I'll ever stop. So this slide is a plug for this event. It happens annually, barring pandemics, of course. If you don't want to wait until probably 2022, you can check out the complexityexplorer.org, where they have a lot of free resources on nonlinear dynamical systems theory, on agent-based modeling, game theory, and stuff like that. But that was in 2019, and I remember it fondly, and it was a very good year. 2020, on the other hand, was an absolutely terrible year. Still is a terrible year. Started out with bushfires in Australia ravaging wildlife. Soon afterwards, we got tipped into this alternative pandemic state, and as we see, it's sort of hard to get out of this pandemic state again. We're about to go into second lockdowns. There's been social unrest. George Floyd's death sort of caused global outrage and protests around the world against systemic racism, police brutality. The climate, of course, never stops to surprise us. Deforestation is higher than last year. And sort of believe that, because the rainforest generates its own water, at some point, if you deforest too much, it can't do that properly anymore, and you have runaway deforestation. So there's a certain tipping point after which the system, because some internal feedback mechanisms, it gets into this deserted state rather than stay in a nice rainforest state. Similar thing with the ice sheets. The Laptev Sea is not refreezing currently. Usually it does. It doesn't do so now. And the problem here is, again, one of feedback, right? So if ice freezes away, the albedo gets weakened. So it's because it's not white anymore. The sun is reflected less strongly back. Local temperatures rise. There's more melting. So there's sort of feedback loops that push it into an ice-free state. Lenton talks about this briefly. This is a nice paper on tipping points in climate. Otto talks about tipping points in social systems, where they try to think about what interventions you can make that have a positive, nonlinear positive change that has feedback. So, for example, if renewables get cheaper than fossil fuels, then there's going to be market forces that push that hopefully in a better state. This tipping point is kind of cool, and I'll be much more formal later on. I just want to have a meta comment here that there's something interesting between dynamical systems concepts like tipping points, critical transitions, and so on, and storytelling on the other hand. So I told you some story about protests and sensitive interventions and so on and so on. So I want to just park that here. Carpenter et al. And Skeffer is there, and a lot of eminent ecologists make this connection quite directly. They talk about, when I talk about Brexit, talk about gender fluidity, Gilets Jaunes protests, from the lens of this complex systems, very simple dynamical systems view. So just as a meta comment to beware of these simple translations. A brief history. So bifurcation theory studies how systems change qualitatively as parameters are varied, underlying parameters. So for example, the deforestation, in a toy situation, I change the deforestation rate a little bit, and then the system can change qualitatively quite dramatically by going into this deserted state. In the 70s, René Thom developed catastrophe theory, which is now sort of part of bifurcation theory. And it describes how low-dimensional systems can change suddenly. And it's popularized by this really very intriguing essay by Christopher Seemann in 1976, who applied it to everything. So he was a master storyteller. He talked about aggression in dogs. He talked about the stock market crash. He talked about anorexia nervosa. He talked about cathartic release from self-pity. It was oddly specific. And he used sort of the CASP catastrophe model to enlighten all these very complicated topics. I'm going to talk about this model later in detail, but just as a historical event, this was quite important. And again, this connection with storytelling. There's a lot of core concepts in catastrophe theory, and we'll talk about them in detail. So multiple stable states or stable equilibria, critical slowing down. I'll define this later. Sudden jumps, hysteresis. So it's hard to go back to this other state. Now, proponents of catastrophe theory pushed it a little bit too far. So catastrophe theory has been described as this great intellectual bubble, and in the 70s, Sauer and Sussman offered sort of prominent critique, chiefly that there was an excessive reliance on qualitative model evaluation. So Seemann and other people would just plot the thing and say, there's some nonlinearity, there's some sudden jump, there's increase in autocorrelation, without quantitatively evaluating those claims. And you see that sometimes in ecology and also in psychology. There are improvements to this, and there's quite some interesting work using catastrophe in psychology. I think it's mostly Han, in his corner doing cool stuff. But we'll talk about this later. So catastrophe theory was sort of important in this tipping point study, but would put it on the map. Critical transitions, early warning signals, I think for me and for many other people was a couple of papers by Scheffer and colleagues in Science and in Nature on anticipating critical transitions, early warning signals for critical transitions. He wrote a very good book in 2009, which I recommend, very nuanced on the topic, and that spurred a lot of research, in climate science, in ecology, also in psychology, on whether we can use early warning signals, critical slowing down, to predict sort of onset of depression, shifts in symptoms, sudden gains and losses in psychotherapy, severe transitions in chronic disease, and so on and so on. There's a lot of, it's in the air somehow. And what I want to do today is to unpack this a little bit. In particular, I want to talk about some core concepts: multiple stable states, bifurcations, resilience, stability, critical slowing down, early warning signals. And I'm going to spend quite some time on this. So if you're familiar with all of this, I apologize for quite lengthy introductory remarks, but they will be crucial for us to understand the nuances and limitations of critical slowing down that have important practical implications. So after introducing some core concepts, I'll talk about limitations, nuances. Then I report briefly on a simulation study we did to sort of see, well, if you want to do this in an online monitoring setting, if you want to observe some systems, a lake or a patient, and you want to monitor early warning signals, how well do you anticipate a potential transition, and what are the factors that influence that? And then I want to offer some, some thoughts on how to move the study and the application of early warning signals forward. Okay, so a lot of stuff. Again, it's going to take a while. Feel free to drop out whenever you need to. So let's talk about some core concepts. Now, differential. So dynamical systems are sort of systems that change over time, and differential equations are sort of the most prominent, dominant way of modeling how systems change in the natural sciences, in the engineering sciences. And they relate how a quantity x, say a population, changes over time, so derivative dx dt, to itself. So it's some function of itself. Now, this equation implicitly encodes how x changes as a function of time. So, for example, I give it, this is a deterministic equation, there's no noise here, there's no error. If I give it some initial condition at time point t0, say it's x0, I know where the system is at any time point t, because you could just compute forward. Because I can say, okay, at x naught, it has a certain rate of change and certain direction. Then I move forward, and then I have a new point, and then I do the derivative thing again, and then I have a new point, and so on and so on. It's implicitly encoded in here, and we call xt, x is a function of t, we call that the solution to this differential equation. Okay, let's look at an example. Maybe I'll try to speak slightly slower, because I think I don't get any feedback, but I have the sense that I'm talking quite quickly. Okay, suppose a population X of birds, humans, worms, whatever, grows according to the Malthusian growth model. So the Malthus was the first to write this down in the end of the 18th century, and he wrote it down like this. He said, well, let's suppose it grows like this. Okay, what does that mean? Let's study this a little bit. Let's plot this. We see, okay, it's a line, it's a linear function, it's a line. You have x here on the x-axis. You have the rate of change, the xt, on the y-axis. Now let's think about it a little bit. Okay, let's say we have 2 units of population, whatever, say 2 humans or 20,000 humans. Let's forget about the scale. Say we have some 2 here. It means, okay, the rate of change is 2. So it grows. It's not negative, It's a positive number. So it's positive change, positive growth. So we're at 2, which means we grow again. So suppose we're at 4 then, and then at 4, the growth is 4. It is larger now. If we're at 8, it's even larger. Now, if we look at the solution to this differential equation, which is now going to be a function of time. This is time, 0 to 10, arbitrary scale, 0 to 10. And this is x, this is the population. You see, indeed, is the exponential function, it's rapid growth. You started with some initial condition, say 0.1, you grow. At some point, you just grow really steeply, you ever quickly, like this, you go very quickly. Only economists believe in this stuff. In the real world, you have resources that limit the growth of a population. So this is not a particularly realistic model of population growth. Let's make it slightly more complicated. Verhulst, I'm not French. He was a Belgian guy. I don't speak French. Pierre-François Verhulst, I'm sorry. Read the paper by Malthus and said, guys, this is nonsense. And he wrote down this equation, the logistic equation, very famous, a logistic equation. And he sort of said, well, we have an x, okay, but we just multiply it with some other stuff. You multiply with 1 minus x divided by 10 here, or k, usually it's k for carrying capacity. Here I pick 10 to be the carrying capacity. Let's plot this again. It looks like this. So it doesn't smash into infinity, but it grows at first. You see, it's high, grows at first. At some point, there's some maximum of growth at half the population size, and then it decreases. Growth decreases. We go down here, right? We go down here as the population increases, and at 10, we end up there. We don't go into infinity as we did in the previous model. We end up at 10, which is the carrying capacity. Now, I've got to do this in the other model, but what you can study here, and what is interesting qualitatively, are sort of equilibrium points of that system. When does the system not change anymore? That means when is this guy 0? So you set it to 0, and you see, well, it's 0 when x is 0. And you have that here, and I indicated with this dot. It's an equilibrium point. You also have an equilibrium point at 10. Why? Well, if I do 10 times 1 minus 10 divided by 10, 10 divided by 10 is 1, 1 minus 1 is 0. The 0 times 10 is 0, 0 growth, 0 change, equilibrium point. Now I can ask, and this is important, is the equilibrium point stable or is it unstable? What do I mean by that? If I perturb the system is at equilibrium. If I perturb it a little bit, does it go back to equilibrium or does it move away from equilibrium? Let's look at this here. At 0, 0 population, nobody's there, no humans, nothing, no rabbits. Say I add 2 rabbits. Now they start to have sex. You can't avoid it. There's going to be sex in this model, and then there's going to be offspring, and then there's going to be growth. It doesn't go back to 0. If you add 2, it increases. It doesn't go back to 0. okay, unstable. 10, on the other hand, is stable. So what I do here, say I'm at 10, and say I just kill 2 rabbits, you know, screw them. And then I'm at 8. Now at 8, there's still a positive growth. So I get bigger again. I go here, I go down here. I go to 10. What happens if I add 2 rabbits to this population? You have to imagine this, I didn't plot this here, but you have to imagine that this line goes down, goes down, and so you have a negative value here for the rate of change, which means there's negative growth in a sense, right? So you go back to 10. Basically, the resources cannot sustain more than 10 frogs, rabbits, whatever. Okay, so that's a stable point, and you see this when you solve the differential equation, and you study it as a function of time. You indeed see that, you know, at first, you know, you grow, then there's maximum growth here at the half point here, which corresponds to this guy, and then you asymptote towards the carrying capacity again at 10. Okay, this is how, you know, usually how things happen. You have some resources, and you can't just use more resources. We only have one planet, and at some point we have to asymptote. Now, so it's better than the other model, but it's not perfect, or well, perfect. It's not particularly realistic because usually you have, for example, predators. Suppose these are just some birds, some worms hanging out in the forest. They're not alone. There can be birds, and birds can prey on them. So let's take this into account a little bit. So let's enlarge this differential equation, and what we do is we add a predation term, which depends on P, which we say is the predation rate. So it's proportional to the amount of birds or the viciousness of the birds and so on and so on. And you subtract this here. The precise functional form, for our purposes here, is not that important. It's a classic paper in ecology that you know, if you're interested, you can take a look. But just to see, we're basically subtracting some stuff that depends on some parameter P. Now we're interested in not so much in the time evolution that comes later, but in the qualitative properties of this system. What are its equilibrium points as we change P? Now, how do we get the equilibrium points? Previously, it was kind of easy, right? You could sort of see here, okay, x is 0, x is 10, you're done. Here, it depends on some other term. There's a sort of graphical trick you could do is you could just plot both terms. So here I plot this guy, and then I plot another guy with some value that I pick now, 1.2. And then when they meet, you know, when they meet, they're equal, which means when this guy is as big as this guy, you subtract, they die, there is 0 change. Okay, so I did this here for 1.2, it's just some value. Well, you see, there's always this unstable fixed point, unstable equilibrium, fixed point equilibrium. I use them interchangeably. And there's some equilibrium points here. You know, it's not at 10, and it kind of makes sense, right? If there's no predation, it would be at 10, but we have predation. So I mean, the bird's going to kill some worms, so it goes, the equilibrium point goes down. So it's 8.2 or so. Okay, this is for a fixed level of predation. Now I change the term here. I say 2.2, and something interesting happens here. Is that, you know, this curve changes. I mean, it's this term I'm plotting, right? It's the blue thing. It goes up and it goes here, and it doesn't touch the curve only at 2 points. It touches them at 4 points. So we have again the unstable equilibrium, the stable equilibrium, another unstable equilibrium, and another stable equilibrium. So here we have 2 stable equilibria. And, you know, we can play this game a little bit more. Let's suppose we increase predation rate even further. This is the green line. You see, okay, here you have a equilibrium, here you have an equilibrium, and then here you have an equilibrium. So these 2 guys merged here. You see that? If I increase the line, and I go, this guy goes here, this guy goes here, and here they meet. Okay. This is for 3 selected values of P. But P is, you know, it's a continuous parameter. Say it varies from 1 to 3. And I'm sort of interested in studying these changes a little bit in more detail. What I can do is I can plot the predation rate P on the x-axis, and the equilibrium points on the y-axis. So I call them x star. These are the equilibria. Here, the solid lines, note that the solid lines are stable equilibria and the dotted lines are unstable equilibria. So let's see whether we've done something wrong here. No. So I plot 1.2 here. You see, okay, here's one stable equilibrium, which is at 8.2. And then there's an unstable one at 0, right? At 0 here. Okay, let's move further. And this doesn't change. This doesn't change much. It doesn't change for 1.5. Doesn't change for 1.6. What you see here is that here the system is qualitatively different, and we saw it here already at 2.2. We have a stable fixed point here at 6.5 or so. This is 6.5, let's say. We have an unstable point at 2.2, let's say, which is here. And then we have another stable point down below, which is this guy. Okay, interesting. If I go further, 2.6, I'm here. And now these two guys merged. And here it looks like we're standing on the precipice of something very dangerous. If I were to change, this is a predation rate of 2.6. If I were to change it slightly, you see that, okay, I moved this a little bit to the right. Well, this fixed point, it vanishes. It's not here anymore, right? There's nothing, there's only white space here. What it means for the system, it does it, it's crashing down. It's crashing down. So we have a critical transition. And I'll show you this on the left in a moment. First, note that here there's no notion of time here. I'm talking about equilibrium states. And equilibrium states are those that I reach, if time goes to infinity. If I now plot this, so I plot this now as a function of time. Okay, t is on the x-axis. Crazy enough to have a double x-axis plot. So excuse that. Later you see a double y-axis plot. A little bit diversity here. But okay, so what am I doing here? I change the parameter p slowly as a function of time. So I change it from 1 to 3. I change it in a linear line very slowly. So what you see, and I simulate the system. So I give it some initial condition. Remember, we need an initial condition, and then we just compute forward. Initial condition here is 8.2 or so. And then I'm in an equilibrium state. I added some noise, just for you to see. Okay, I add some noise, and then there's some scattering around the line, and you see that this line tracks very nicely, the theoretical equilibrium, right? So we track this equilibrium. We track it. As p changes, right? P is 1 here, we're at 8.5. So p is 2.2, we're at 6.2, as we said earlier. We just go. But at some point, I do a tiny change in p, and suddenly the system crashes down close to extinction, right? Bam. That's a sudden transition. We call it critical transition. And what's especially pernicious about this system and about the Arctic ice sheets and about the Amazon rainforest is that it's hard to reverse. Once you've passed this point, and it's hard to go back. Now imagine, you can see this here easily. So if you're here, suppose you go back, you kill the birds. You don't want them. You want your worms. Yeah. If you're that kind of guy. So you want the worms back, and you decrease the predation rate, you decrease it, but you're on that fixed point here, and nothing's changing here. You're on that fixed point. And only if you go very far back, you kill a lot of birds, did some bad things, then the worms come back. Then there's another, what's called technically a saddle node bifurcation that pushes you up. And you can also simulate this. So I simulate here, I start from here, and I go back, and I don't jump up. Then life would be easy. Then you could just, it's easy to reverse. But here you have to do a lot of work until you get back to your wonderful worm population. Okay. Let's look at a figure which is from our paper. This is figure 1, where basically, we went through some steps, with exponential growth, with logistic growth with predation, and now we zone in on this model we had with the worms and the birds. And this is the bifurcation diagram here, right? This is the same as just nicer, and you have the gray to indicate the bistable region. And say you have two ecosystems, and then for one, somewhat the predation rate is about maybe 1.7, okay, and the other ecosystem has 2.4. And what you see, and they differ in interesting respects. So what you see is, okay, this guy is much closer to the tipping point, right? If I were to increase predation by 5, it would crash. If I increase predation by 5 here, it wouldn't crash. And so this, we call this system here is a sort of a higher resilient system, and this is a lower resilient system. And one other way you can visualize these unidimensional systems is by virtue of a potential as a stability landscape. So you can as a ball in a cup diagram, they're very popular. This is the state, is your population, and this is sort of the landscape, and what you see is this ball seems much safer than this ball. And by resilience, we define resilience as the extent of the perturbation the system can withstand before moving away from its equilibrium point. So if I look at this worm population, and I have to kill a lot. I have to go until here, basically, until I don't roll back anymore. Right? I basically have to kill until 2, and then I'm basically in this other stable state. Here, on the other hand, I kill like 3, and then basically I roll into this other state. And that's an interesting concept, resilience. To think about it in these simple systems is the extent of the perturbation you can withstand. Now, that's what you care about in a sense, right? You want to know, okay, how robust is my system? What happens if some birds come? Are all my worms going to die? But it's hard to use that in practice to understand whether you're close to a tipping point, because if you have a mathematical model, then you could just kill half of them, and we do that later. But and you can see the result. But in reality, it's kind of weird for you to kill your beloved worms until they don't recover anymore, and then you say, that was the point until I which they could withstand these perturbations. But then you're out of worms, you're out of luck. Weird example, by the way, but we're worm lovers here, and so resilience is a little tricky. What's more interesting is stability, and stability is so that the recovery time is proportional to the recovery time. So suppose I push this guy up here, then intuitively you look at the slope, you should roll back to your equilibrium point rather quickly. Okay, if you do that here, it's gonna take you a while. So stability is proportional to the recovery time. You can see that I'm solving the system here. So here I'm simulating from the system over time. Okay, I'm simulating it. It's at equilibrium. I'm not changing P. P is fixed at 1.7. I'm simulating from it. It's in equilibrium. At some point, T30, I just kill half of them, I just do it. And what you see is that they bounce back quite quickly. This intuition here, of 8, I kill half, I'm at 4, I roll back rather quickly. The other worm population, I'm at 6, I'm gonna kill 3. It's gonna take a while until I roll back. This is what you see here. They recover rather slowly back to the equilibrium. This idea that as you approach, look, that this ecosystem is closer to the tipping point. As you near the tipping point, stability decreases. Your rate of recovery is longer. There's a critical slowing down happening. Okay, that's the technical term, and that you can see in a number of early warning signals. So the early warning signals based on critical slowing down. For example, variance. If you look at this system, You just look, and I'm simulating here. You see, I add noise. I add noise, and noise we need actually. Otherwise, noise is always there. We're not always completely in equilibrium. There's always some noise happening, always some perturbations, and these help us actually when computing early warning signals. So I have noise here, okay, always, and I'm around this equilibrium, and it's not particularly high variance. If I go here, I have a higher variance. You see, sometimes I go up here, and I go down here, and the intuition is again, if I have a shock here, I go here. It takes me a while to go back. Say I have another shock in the same direction, then I go further away compared to here, where I return much quicker to equilibrium. Similarly, there's an increase in autocorrelation, which I've plotted here, between the state at time t and the t+1, because this guy returns slower to equilibrium, right? It's just that system states are more similar to each other, and so there's an increase in autocorrelation. Okay. Now, Wissel sort of was the first to sort of describe this. He was a physicist. He called it a universal law of slowing down near saddle node bifurcations. So saddle node bifurcations, again, is where two equilibrium points collide and then they vanish. So he found this critical slowing down, and he also did some experiments. And this has been observed in wonderful experimental studies. So Dai et al. 2012 studied yeast populations. Nobody cares about yeast, so you could just kill them. And they mapped out the bifurcation diagram experimentally. So you have some yeast, in some medium, and then you increase the dilution. So you have the yeast in some medium, you put it in some other medium, but then there's more water or more salt, and that amounts to an increase in death rate. So basically, it's, think of it as predation, where we are the predators. The dilution factor is the predation rate. And then you can sort of just see, okay, well, here dilution factor, they are quite robust to noise. If I dilute them and then I do perturbation, they go back to this state. And so I can map out the bifurcation diagram experimentally. So here, for example, if this dilution factor, say dilution factor of 1,000, and then I'm here, and then I kill this amount, it goes back, kill this amount, it goes back, kill this amount, it goes back. At some point, it doesn't go back anymore. So it has crossed this unstable fixed point. So they map this out experimentally very nicely, and they find early warning signals before the tipping point. So here in this system, there is a tipping point. If dilution factor is 1750 or what, then I crash, the population goes extinct. And here indeed they find an increase in autocorrelation, an increase in standard deviation, increase in the coefficient of variation, which is standard deviation divided by the mean. Not so much in skewness, but so yeah, they mapped it out experimentally, very nice, to sort of, because this is all theory, yeah, and they showed this experimentally. Wissel also, this is known, but they did a nice experiment. Another area where this is being applied, has been applied quite frequently, sort of in observational studies, especially in climate. So, the Earth's climate has transitioned historically in the past. So, for example, at some point, the greenhouse Earth, where there were no ice caps, ended, and then we had ice caps. And this is shown on the left. On the right, within ice ages, where we have ice caps, there are periods, glaciation periods, where it's warmer, where it's cooler, and they vary. And what you see here is some relevant variable of interest. You see this thing, and you'd say, you look at it, maybe you linearly interpret what you predict. You'd sort of say, it's going to be fine, no danger ahead. Similarly, here you'd be like, nothing's bad, it's going to happen. But if you looked at the autocorrelation, you'd be like, maybe there's something going on here. Maybe we're nearing a tipping point. Not as much here. Here's stronger. And the way you do this usually, also how it's done in psychology, sometimes you do a rolling window. So you take here that just took this time series, they computed the autocorrelation. This gives one data point for the autocorrelation. They move a rolling window one step further, compute the autocorrelation, and so on and so on. So it's a non-parametric way to estimate a change in autocorrelation. And they find an increase here. Lenton looked at this in 2001 in some review article, also on early warning signals in climate, looked at this particular transition. What is important is that you also look at, well, how sensitive is this to sort of my rolling window size? the bandwidth of my filter. Usually you filter this data because there's some, I don't know, seasonality, some high frequency stuff you want to get rid of. And you can plot it like this. So then you have a surface, right? You do the same analysis, but with different sliding window, with different filtering bandwidth. You can sort of say, okay, here I have a very high autocorrelation. But if I'm here, for example, it's much lower, or here. It gives you a sense of how robust your finding is. For the autocorrelation, it's quite good. For the variance, it's great stuff going on. And so from theory, you would expect that both autocorrelation and variance goes up, as we've seen earlier. And indeed, Ditlevson and Johnson sort of argue, actually, this was just due to some noise. It's not a bifurcation-induced tipping, it's just some noise. Similarly, with experimental studies, you don't have that, but with observational studies, you're conditioning on the fact that the system transitioned, and that increases the false positive rate. And Boutica and Hastings looked at this. I think, I don't want to get into this too much, but Boutica and Hastings, everything by Hastings or Boutica on early warning signals, I can recommend highly. Very good stuff. But okay, just to give you some examples where this has been applied, experimentally, observationally. Okay, let's do a recap of this introductory stuff before we get into some nice nuances and limitations. Now, some systems can exhibit multiple stable equilibria, and we've seen this with yeast, and we've seen this in our model for worms and birds. And usually it's because there's some feedback happening. So the Amazon rainforest, there's some feedback that it generates its own rainfall, ice caps, albedo is reflected less strongly, the sunlight, so you have warming and then it increases. With yeast, it's interesting, you have some collaboration in how they eat. So there's an Allais effect where the fitness of the population depends on the population size. So if you cross a particular threshold, then they can help each other and then they grow. And if you cross the other threshold, then they can't help each other and then they die. That's why you have these multiple stable states. Now, in these systems, equilibria may collide and vanish, and that's the saddle node bifurcation, or a tipping point. Usually, colloquially, it's referred as a tipping point. And then you have critical transitions and hysteresis. So stuff is hard to reverse. Resilience we've defined as the extent of the perturbation from which the system can still recover and return to its equilibrium. Stability as the rate with which it recovers to the stable equilibrium. So how quickly do I go back? And I'm telling you about unidimensional systems. In the real world, it's of course much more complicated. But it's important to have some intuitive understanding of this. As the system approaches a saddle node bifurcation, stability decreases. So the system returns more slowly to the stable equilibrium, and that gives this phenomenon is critical slowing down. And it gives rise to a zoo of early warning signals: autocorrelation, variance, kurtosis, skewness, cross-correlation, spatial variance, dominant eigenvalue of the covariance matrix, a lot of crazy stuff. Some of which are more motivated, others not. But that's just, as a first block of information for you, just to be aware of some core concepts. And now we'll go into nuances and limitations. And I mean, this was the longest part. So rest assured. Okay, critical transitions that are hard to predict, hard to reverse. We care about them, right? We care about them in nature, we care about them in society. And early warning signals have the potential to signal critical transitions. And now the question is, what types of errors could we make? Now, first, you could signal a critical transition, even though no critical transition occurs. So it's just a chance pattern. Or there could be some systematic stuff going on. The early warning signals actually occur also prior to non-critical transitions, and we'll talk about this. So that's a false positive, basically, if you want to think of it in that term. But then you can also have a false negative, where you fail to signal a critical transition, even though it does occur. And this can be due to many reasons. I focus on a few of them in the paper. Here, I just want to focus on two. So let's tackle this first a little bit. So let's tackle the first part first. Now, okay, early warning signals prior to abrupt transitions. We've seen this bifurcation diagram before, right? There's hysteresis, there's a saddle node bifurcation, drops, hard to reverse, drops Okay. I can play with this model a little bit and decrease this region of bistability, and then it's not there anymore. And what you see is that then there's no hysteresis, right? If I'm here, I increase the predation rate. I'm just going to be down. There's an abrupt transition in some sense, right? It's quite quickly. I mean, it's not linear, but it is. But there is no hysteresis. Okay, so these transitions are easy to reverse in theory. what I can do, Kefi has done this experimentally with simulations, but you could do this analytically. You could derive the autocorrelation as you increase the predation rate. And as I sort of argued before, at the cell not bifurcation unit, autocorrelation is sort of 1 in unidimensional systems. So it increases, right? So here predation rate, you at 1, you kind of fine, you move. What happens to the autocorrelation? You increase. And there's a nice symmetry here, right? If you're here and you're interested in sudden recoveries, you want to predict when an ecosystem recovers, you could also use, if it follows the cell not bifurcation, you could go the other way, and there's also an increase in autocorrelation. Similarly, you have it on the right? You also have an increase in autocorrelation, going to 1 even. And there's also some symmetry here, but there's no hysteresis. Okay. So early warning signals, critical slowing down is not specific to critical transitions with hysteresis. Yeah, that's okay. Good to know, but not earth-shattering. However, it can also occur sort of during or prior to smooth transitions. So there's another note. I've rescaled the predation here from 0 to 2 rather than 1 to 3. Doesn't really matter. This is a different model now. What you see is here the equilibrium point changes linearly as I vary the predation rate. Okay, changes linearly as I vary the predation. And here there's not even a bifurcation. So I played with this model a little bit more, and then you get something like this. There's no, there's no bifurcations. Slightly a little non-linearity here. Okay, now what you see is that the autocorrelation and the variance also, all these early warning signals increase here even to 1, also before this transcritical bifurcation. Okay, so, and also here, it doesn't go up to 1, but it increases to 0.8 for this model, before this non-linearity here. Now, that's a nuance, it need not be a bad thing. So for example, in infectious diseases, if you look at the simple SIR model, you realize that there's a transcritical bifurcation when R0 is 1. So when outbreaks become possible and the epidemic can actually be seeded, can be stable in the population, there's always going to be some virus circulating rather than being eradicated. That's a transcritical bifurcation. So if you go from 0 to 1, then 1, you have that increase. And that might be interesting to predict also, even though it's not a catastrophic transition, but it might be interesting as well. Here, you could sort of say, there's not going to be a critical transition, but still it's interesting. If I look at from 0 to 0.5, so here I'm at 3.5. If I'm at 0.5, I'm at 3. Okay, there's a half a population changes by 0.5. However, if I do an intervention here, in theory, if I could, I actually kill the population by 1, say. So in a sense, they're very generic. There's some instability maybe here that they also anticipate. So it might actually be nice in practice. But if you just wanna, if you're here and you just think, maybe there's going to be a critical transition. I mean, there's not going to be a critical transition. The mean, you could just use the mean, and you'd have a good prediction of the future. Okay. So some nuances here. There's another nuance which I like. It's very interesting. Is that, and I gave you the intuition before. The critical slowing down is a loss, is a result of the loss in stability, right? The recovery time takes longer, you're critically slowing down. And we usually take this to indicate a loss in resilience. However, this positive correlation need not hold. Just as a reminder here, this is from Dai et al. 2015. I have this landscape, stability landscape. The system is here. The resilience is basically, okay, how hard can I push this population, yeast again, our friend, population of yeast before it goes extinct? That's the resilience. The stability is sort of, again, proportional to this local curvature here. And so if I simulate from the model again, this is just here, and I make an intervention, this is sort of the recovery time, sort of proportional to stability, and the resilience is the extent of the perturbation I can bestow upon this system before it dies. So I push it. I can push it until here, it's fine. But if I push it too far, if I push it past this unstable fixed point, it goes extinct. Now, died out 2015, I think is a brilliant study, and I can imagine how they thought about it. In 2012, they killed the yeast by increasing the dilution, and I'm sure died and said, well, why don't we kill it by reducing nutrients? And it's surprising what you can learn by doing these simple system experiments. And what they find, this is a schematic illustration of their finding, is that, depending on how you kill it, the relation between resilience and stability changes. So at the fault bifurcation, at the saddle node bifurcation, the same term, you have zero resilience, zero stability, and you crash into this other state, right? Say you start at an initial condition where you have high resilience, high stability. Yeah, you see, you have to push it quite far to go back, and the local curvature is quite high. Here's why this is excellent. So what they do is they increase the dilution, and you remember they did this in 2012 also. They increase the dilution, which amounts to increasing death rate, and this is this driver 1. And what you find is basically you push this guy down, okay? You push this guy down, and if you push this guy down, the stability does change. The stability changes, but the resilience doesn't really change, right? The perturbation still has to be, quite large to push the system in the other state. So stability changes quicker than resilience, and stability is what you see in critical slowing down. So critical slowing down will say, yeah, rising autocorrelation, rising variance, and then this might be a good driver, so to say. If you reduce nutrients, they also die. There's also cell non-bifurcation, but the potential changes in a different way. So here, this guy gets pushed like this. It doesn't get pushed down, it gets pushed to the right like this. And if you do that, the local curvature doesn't really change here. So there's still high stability, but there's low resilience. So high stability means critical slowing down doesn't occur, which means you don't see early warning signals, so you don't see them so pronounced. And that's indeed what they observed empirically, that reducing nutrients, you don't find early warning signals, or you don't find them as pronounced. And that's important, I'm talking about this later as well, to think of, well, what's the underlying thing that sort of changes the state variable? What's the driver of the system? And what they also do, in another stroke of genius, they actually combine the dilution and the reducing nutrients. And what you can then find is basically they show that you go first here, you have a low stability. So here we sort of find critical slowing down, but then you go up, and then you go up, and as you decrease your resilience, we go to the left, you actually increase your stability. So you'd find decreasing autocorrelation rather than increasing before a tipping point. And I like this study because it's a very simple system, unidimensional, but already here you sort of see, okay, there are certain nuances I have to take in mind. And usually you don't have just one driver acting on the system, but you have 2 drivers or 4 drivers. So I think this is a nice demonstration. Still, this is a unidimensional system. State variable is unidimensional, the population size or density. And things get a little bit more complicated when you go higher, when you have a higher dimensional system, which is what we have in the real world. All the time. And there's an interesting nuance, and this is the last one I touch on, I think, is that early warning signals need not be expressed in all system variables, equally strongly, or at all. So Boerlijst, they actually at Amsterdam show this on a staged predator-prey system. So they have a model, and what they have is predators preying on adult prey, but not on juvenile prey, right? So you have two type of prey, and predator preys on the adult prey. Now, at some point, you have a bifurcation, a saddle node bifurcation, and the predator collapses with this critical transition because it goes extinct. And then you basically now you can not only measure the autocorrelation of one variable of the yeast as we did before, but you can measure it of the predator, the adult, and the juvenile, right? And you can look at it, and we've reproduced the results here. As we change the bifurcation parameter, you see a very interesting pattern. You see that the autocorrelation of the juvenile population increases. And remember, the juveniles, they don't really do anything here. I mean, the predators prey on the adult prey, not on the juveniles. So intuitively, you'd think, well, I have to measure the predators of the adult prey. But somehow you have to measure the juveniles. Indeed, if you do measure the autocorrelation of the adults of the predator, you see that it actually decreases. Predator jumps a little bit, but it's too late. So it actually decreases. If the same pattern with the standard deviation, basically you've increased standard deviation with the juveniles, and you have a decreased or constant standard deviation for adults and predators. So that's interesting. And that has, well, so we did this also for multivariate indicators just to see, and clearly, things get funkier because it's some combination of these three. So for example, only for the dominant eigenvalue of the covariance matrix, you have a monotone increase. So this is cov-eigen here. I don't want to get into it. You can read the Chen paper. The spatial variance first decreases and then increases. The cross correlations between these components decreases rapidly and then increases rapidly. So there's a lot of puzzling patterns you might observe and are being observed in, they've done studies on lakes, and one variable shows another not, and they're confused. And you might well be confused, right? You study a system and you find autocorrelation in some item, and you say, this critical slowing down, this is important. And then another person does another experiment, finds decrease in autocorrelation in another variable, and says, oh no, but actually we're getting better. And then you have contradicting results in the literature, and then you have to do more studies and so on. Yeah? And that can get out of hand quite quickly. But if you understood the system and you just looked at it, and then you would realize, critical slowing down need not be expressed in the system variables equally strongly or at all. And so that's quite interesting. There's some technical details why this happens that I don't want to get into it. Odea and Drake 2018, if you're interested, do this formally, and they show what happens, and they apply this to an infectious disease model, a SIR model, and they actually find that you should measure the autocorrelation of the infected and not of the susceptibles as an indicator for when you have an epidemic threshold. So it's an interesting nuance that you have nuances when you're in unidimensional case, but you have even more nuances when you're in a high dimensional case. Okay, so let's do a little recap here. The theory of critical slowing down is both general and nuanced. It's not specific to critical transitions. So critical slowing down occurs prior to all zero eigenvalue bifurcation. If you want to Google this, this is the term. And they can occur during smooth transitions or before transcritical bifurcations. And this may not be what we desired. So what we desire, if you want to predict the short term, then maybe you could just use the mean, for example. And they're not specific to bifurcation. They can occur due to nonlinear forcing. And that actually, that can be a good thing or bad thing depending on what you want. If you want early warning signals to anticipate critical transitions, then it's not going to work because it's not specific to that. But if you want to think about increased autocorrelation, maybe as some general indication of how stable the system is and whether you can push it into a positive state or negative state by virtue of intervention, then that might work. However, as we've seen here, it can fail due to a number of reasons. So you can have relationship between resilience and stability breaking down if you have different drivers that changes the system. And early warning signals, need not be expressed equally or at all in the system variables. So there's important nuances in the multidimensional case. And there are a number of other nuances. So I encourage you to read the paper. We discuss a few others. There are even more, but there's only so much time you have in a lab meeting, which would usually end now, actually, but I have a little bit more. So this is, we talked about some core concepts. We talked about some nuances, limitations that are important, and that you may not, you might not get this when you read the big papers. Usually, it's known, right? You have a first study, you get a large effect size, and then you do the study again later, 5 years, and you realize, actually, there was some selection bias here. And that's, that it's just that as you learn more over time also about these phenomena, okay, they're more nuanced. Okay, these are sort of the theoretical considerations that we tackle in the paper. There are also practical considerations, and I want to briefly touch on them. So there's, there is a potential of early warning signals, and they are being discussed in ecology, conservation management, in psychology, clinical psychology, as a sort of potential as an online monitoring tool. So, for example, you could monitor a patient, or you could monitor a lake, and then you say you have an increase in autocorrelation, and you say, oh yeah, maybe this is a bad transition, I want to intervene to prevent this transition. Or you could say, if you're in a bad state already, there's an increased autocorrelation, you'd be like, this is the time to intervene, so it can bring about positive change. But that is, if you think about it, that's a difficult statistical challenge also. So you sort of have to monitor these early warning signals in real time, right? You have to query the system, get the autocorrelation as the system sort of, bumbles along. And then at some point you have to say, well, when do I indicate a transition? And what factors influence the performance of this in practice, right? And here we do a simulation study where we take a sort of simplified toy model that has been used by others in psychology, and it's sort of a nice illustration of these critical transitions. So you have 4 variables. Say these are positive states, these are negative states, and this is the bifurcation diagram. So there's one parameter R that sort of, if I start here, it's sort of in a positive state, and I move along, say in healthy state, and move along, and move along, and move along. At some point, there's the settle node bifurcation, and I drop into, positive state is low and negative state is high. So here I'm saying unhealthy, depressed, and it's hard to go back again because of this hysteresis. So this is like in some sense, it's an ideal model where critical transitions can occur, and you can simulate this. Over time. And here I show this illustratively. So you have here, you have the system variables, they vary. And I change R over time, as we did before with our worms. Here's at 0.6, it stays at 0.6. At some point, I'm like, okay, this guy's going to transition. So I initiate the transition. And then at some point, it touches 1.2, and here's the settle node bifurcation. And the person gets depressed, the lake goes bad, worms die, stuff like that. And if I do this in real time, I have to, first of all, I have to have some baseline. That's also problematic if I want to do within subject thing, right? I have some baseline where I can compute the early warning indicators, say I compute the autocorrelation or the variance or the cross correlation. So I have some baseline where I do that. So I take a rolling window, I compute the autocorrelation at baseline, and then I have many autocorrelations at baseline. I take the mean standard deviation, and this is sort of my benchmark. So okay, this is at baseline, this guy has 0.4 autocorrelation, and then I observe him transitioning, and as we transition, I get more data, right? I get more data, and here I also do the rolling window. At each time point, I get an autocorrelation. Each time point, I get an autocorrelation. So this autocorrelation will increase close to the tipping point in this ideal system. It will increase. And then at some point, I say, okay, it has increased enough. I will intervene, or I will signal a transition. So, okay. So the question is, how well can we do this here for this system? What factors can we vary? Well, there's a ton of early warning signals. So I'll some chat stuff. Yeah. How well do early warning indicators anticipate transitions. Can vary the type of early warning signal, right? Autocorrelation, variance, cross correlation, you name it. I can vary the noise level. I can sort of say, okay, there's a lot of noise in the system. There's less noise. There's extreme noise. This could be measurement error. This could be other sources of noise. I could vary the extent of the baseline, right? I mean, it doesn't matter whether I have 25 days of baseline and I have 1,000 days of baseline, because I'm comparing the early warning indicator that changes to that baseline. And if I have a lot of uncertainty in the baseline, then it's going to be hard to detect the change, even if I have even if a lot of observation in transition. Sampling frequency, of course, time to the tipping point. How long does it take the system to change, to go to the tipping point? And then the decision threshold, importantly, right? So here we vary that in the sense that, okay, we compute the early warning indicator at baseline. We compute the standard deviation, so the mean and standard deviation, and then we compute sort of this running autocorrelation, and then we sort of say, okay, if it's larger than mean plus 6 times the standard deviation, we indicate a transition. And so there are various decision thresholds you can study. Yeah, many people have to go. Then I think it's fine. I'm just gonna talk a little bit more, 15 minutes or so. I mean, feel free to ask questions now. We can talk about it now, or I am the host, Danny. I think it's fine. I mean, I'm happy to just go on, and because this recording might be useful for other people, so I'm just going to go through with it. But if you have questions, I mean, again, please don't hesitate to answer them in the chat. So okay, so we change this here. Okay, confusions. All right, so we can change the conditions here. Sample 10 times a day, noise with 6 or 5 times, it sort of changes just to illustrate. And you have less baseline, you have more tipping point, more baseline, even more baseline, and so on and so on. You could sort of ask yourself, okay, how well can I anticipate a transition? So you simulate say 500 times where the system doesn't transition, and you simulate 500 times where the system transitions, and then you ask for these various configurations. Okay, Rogier asked a question. Yeah, it's so interesting. So a question, one could also conceptualize stable resilient states as those defined by the same parameter sets, but lower noise. So less likely of exceeding a half by accident. And I think you could do that, right? But it's in a sense, it's less fundamental, because the noise could just be, noise is usually noise. It's some stuff you don't model. So if you're in one, say I'm a person, and I have basically what you're saying is that, okay, if I have two people, and they one is super healthy, the other is super healthy, and then I just insult the guy a lot, push it a lot of noise, and I don't do it with the other one, this system is in some sense less stable. That's a different take. It's less fundamental than the other one, but yeah, it's indeed you could view it like that. More generally, you treat noise as external instead of a property of the system, but two systems could differ. Yeah. Yeah. So I think it's just a different way to view the issue. But generally, so in the literature, in ecology and so on, they define resilience as that, is independent of the noise, and stability is independent of the noise. Okay. Yeah. So okay, you have these systems, you simulate, then you can sort of say, okay, You can look at one particular indicator. You can look at different settings. You can look at noise of 4, of 6, of 8, different transitions. And then you can sort of say, for a decision threshold, so these are ROC curves. For a decision threshold, say, of this is decision threshold of 6, it's very conservative, and you would have barely any false positives. Now, if you and also very few true positives, right? And you could be a little bit more liberal. You could sort of say, actually, I signal it, liberally. This is decision threshold of 1, for example, instead of 6, and then you'd have an increase in false positive rate, but conversely, also an increase in true positive rate. So the decision threshold maps out the curve of your classifier in a sense. And you can look at this here. I dotted it, the black one. I dotted it with 2 sigma. Usually that's used in the literature, so I dotted it here. But here you can compare basically these curves across conditions. And what you see, interestingly, actually 10 and 5 sampling per day doesn't really change much. There's some nonlinearity here where if you do it once per day, you decrease your performance quite a bit. The most important thing here is basically that as you increase noise, the performance gets reduced quite heavily. And I haven't even plotted the noise 10, but this is chance performance. You can also you can look at this for different indicators. Here we have combined an indicator, but here you can look at it for different indicators across different conditions. I don't want to get into this because of time. You could read this more detail in the paper, but basically, just to wrap up, we used wrap up this part. We used the Lotka-Volterra model. It's not a particularly realistic model of any psychological system, and you never see such data in practice. I mean, if you see this in practice, you're done. That would be amazing. You don't see that in practice, and the time scale is sort of arbitrary. I mean, I told you it's for illustration purposes. I say it's 5 days and 10 days, but because we don't have an interpretation of these variables as being grounded in the real world, we can't give the system a time scale. So, for example, if X1 would be sadness, for example, and we knew that sadness changes like this over days or weeks, then I could say, okay, I can ground the system, on a daily or weekly scale. If it were to change on years, then this wouldn't be days, but this would be years, for example. So please don't take away from this that, okay, if I do a 100-day baseline, I'm fine. Rather, these are only valid to compare relatively. So you could say, okay, if I double my baseline, then I have this effect for this particular system. Okay, now there are 2 ways to interpret this simulation study. First, as an illustration of how to study early warning signals in simulation. So if you have a crude model of a system, it sort of shows how you can study the performance of the indicators. And you can sort of vary relevant factors, type of indicator, noise, sampling frequency, extent of baseline, time to tipping point, decision threshold, and so on and so on. And yeah, so that's one way. Another way is sort of, well, maybe this is a little bit dampening our enthusiasm. So in some sense, this is an ideal system. So again, you have a saddle node bifurcation, you have a brutal critical transition, you have early warning signals expressed in all variables, something that you usually don't get in the real world. And here, you still have a poor performance under noise. It's also found by others. And if you have poor performance here, why would you expect good performance in practice? So I don't necessarily believe that it's hard to generalize from this particular model, because the set of all possible models is extremely large and generalization is difficult. But I do think that we have to be a little bit careful in what we think early warning signals can do, especially in this online monitoring setting, which this is how we simulated it. And usually, studies don't do that, but they say it could be relevant for this. Okay, so I'm going to do this. I mean, yeah, so I think we're going to do another 10 minutes or so. And then I'm happy if you just, if you have any questions left, you just post them and I answer them. Or you just email me or whatever. Sometimes I overdo it a little bit, but I do hope that some of this is useful for you. And as I say, it's recorded. So if you're really interested, you could continue watching. Now in the paper, we have we have this flowchart to organize our thinking a little bit more. And basically I want to focus on these three first. There's a lot of data pre-processing steps that are important to take into account. So we saw this Tim Lenton who did this filtering and rolling window analysis, and it's important to do this in practice to sort of get a rough sense of how robust your conclusions are. And this is usually not done in ecology and also not in psychology, and I would suggest that that's an important step. You could combine multiple indicators into sort of standardized indicator. To combine variance, autocorrelation, cross-correlation in one indicator. You could also move away from generic indicators to system-specific indicators. That you buy information by making assumptions. You buy performance by making assumptions. And Boutig and Hastings is a very nice paper on this early on. That sort of says, look, we have to move away from this. But you could also just machine learn the heck out of it, and maybe that's the way to go actually. So you Jacobs and Zhang do this. They try to predict depression severity, using weather, using geolocation, stuff like that. And maybe that's the way to go for predicting transitions. We discussed this a little bit more in the preprint. But all of this, basically, all of this is sort of contingent, on this step here. So are there actually multiple stable equilibria? Are there critical transitions? Are these transitions smooth, abrupt, and what drives these transitions? So Litzow and Hanziker review 94 early warning signal studies in ecology, and they sort of find yeah, so if you guess transition, so there's a question, if you guess transition every time, the success would be 50%. Yeah, that's the line, that's the line you have in the ROC, that's the chance performance. Okay, but so the Litzow and Hanziker review these early warning signals, and what they find actually is that those that have sort of established that there's a nonlinear relationship between the state variable and the driver, there you have a much better chance of finding early warning signals. So they actually, all of the studies they reviewed, and they provided this indication of nonlinearity, had a positive result. The others, was sort of 50-50. And what do I mean by that? I mean, we've seen this before. You have a predation rate here, that's your driver, and you have a state variable, and that's a nonlinear, it's clearly nonlinear, right? And here on the right is the y-axis, double y-axis plot. This presentation is a marathon. What you see is I increase the predation rate slowly, and what you see, so I just increase it linearly here, and what you see is that there is a critical transition, at 2.6, the system tips. We saw this earlier, right? However, you could also just have a linear relationship, and then just there's an abrupt change in your driver, and in your state variable you get this shift. And you could do, if you just look at the state variable and you have an abrupt shift, you do some change point analysis, you instead of say, oh, maybe there's some nonlinear stuff going on, but the system fundamentally is a linear in this driver response relationship, and there's just some shock here. You'll have that. So basically what I'm saying is, okay, it's not enough to just look at the state variables. You need to think about the drivers, and one heuristic way to do this is with the cusp model to close a circle here, which allows for sort of bimodality, sudden transitions, hysteresis, critical slowing down, and gives you a way to think about the drivers of the system rather than just looking at the state. It gives you a way to reason more theoretically about the drivers. So, for example, here. This is in the plane. It's a 3D. So you have the state variable here on the x-axis, and you have here information on this axis, and you have attention on this one in the context of attitudes. And what you see is, you can collapse this in a particular way. So, for example, if you collapse it like this, right? If you have or say the opinion and the information, you'll get, if attention is high, you get a sudden transition hysteresis. And if it's low, you get a smooth change. And similarly, if you cut it the other way, if you cut it like this, then you get a pitch bifurcation. So you have you know, there's this guy is here, one stable state, and then, you know, then there's going to be this pitchfork way of two stable states. And you can test this empirically, right? You could just look at, they did this, they look at attitudes of some students and how towards some statements and how intense they felt that these statements you know, were important. And you cross-sectionally, you could see, okay, hi, actually there's some, you know, there's something happening here with an increase in bimodality. So you try to understand the system a little bit more by thinking in terms of drivers and in terms of the state variable, rather than just, you know, just looking at how the, you know, how I'm feeling lonely changes over time. It's important to look at this, and you know, it's basically in a sense it's a you know, it's a one approach to simplify the problem a little bit. So what we've seen in the first part, and what has been stated in the ecology literature, is actually, look, you have to have some understanding of your system before you apply early warning signals, because it will have an effect whether they, you know, whether they work or not, and which components they will occur or not. So ideally, you know, we'd go the route of ecology, where you have formal models, you write them down in differential equations. But I mean, that's hard, you know, that's hard, and it's hard in psychology, especially because, you know, the problems sometimes are just very high dimensional. So you could do this, for example, for panic disorder. You know, Don Robinot did this, where, you know, it's, you know, if you've had a panic attack before, it's slightly simple, and there have been theories since the 80s, and he formalized it. Basically, you just have, you know, you have some arousal that's increased, and then you sort of think, okay, this could be a threat. You perceive the threat, the arousal increases, and so on. It's a vicious cycle. You loop into a panic attack. For depression, for example, it's much more difficult, right? I mean, you have various outcomes, physical symptoms, cognitive symptoms, mood, sleep. There's very high dimensional space. And this, you know, it will take a long time before you can write that. If you can do it at all, you can write out a system of differential equations that properly account for empirical data. And maybe you just have to do machine learning, right? So that's another approach. But maybe you could also just, you know, maybe you can approximate the system, and they do this in this Ising attitude model, where we know, you know, it's complicated, you have various attitude elements, but, you know, on some coarse-grained level, you know, maybe it's just this cusp where you have two drivers that you can sort of vary and that you can sort of poke empirically. So Kramer also did this in 2016, where he sort of said, look, depression is this Ising model where you have symptoms that are connected or not connected, and indeed you get the cusp where you sort of say, okay, you have if connectivity is low, so if there's not much connection between these symptoms, you increase stress, you'll have a smooth transition. If connectivity is high, on the other hand, you increase stress, you have this cell knot bifurcation, this bistability. And this is something, you know, maybe this is an intermediate step towards actually building proper formal models about these systems, where you can sort of poke, well, does it follow this cusp? If it does, then maybe there is critical slowing down, and it is in these variables. So okay, let me wrap up. This is, again, has been a marathon. So as a summary, dynamical system theory describes how systems change over time. Some systems exhibit multiple stable equilibrium critical transitions. Critical slowing down is sort of the slow recovery after perturbation when close to a tipping point. And that's pretty nuanced. It's a pretty nuanced theory that can occur during smooth transitions, can fail to occur during critical transitions. And, you know, things turn out to be more complicated than they initially seem. And we hope that at least with this preprint, if you read it, you sort of makes you wonder, okay, actually maybe things are more complicated. And somewhat ironically, you know, we didn't expect this when we started it, somewhat ironically, you need to build up a sufficient understanding of the system before you just blindly apply early warning signals. So are there multiple stable equilibria? Are there critical transitions? Are these drivers in stress, attitude, information, are these linear, are these nonlinear? What are the time scales of the system? So, you know, it's a fast and slow system. So the driver usually changes slowly compared to the state variable. What are these? And, you know, everybody says this, and it's kind of, you know, it's kind of true. Sort of to try to build formal models, but that's hard, you know, that's hard. And maybe using the cusp as sort of first approximation might be a good idea. Gives you a notion of how you can think of the drivers, and then you just test this empirically as a first step before building, before trying to build a really proper high dimensional model. If you, even if you have the, early warning signals we've seen performed rather poorly in simulation, mimicking online monitoring settings, and they are linked. They are linked. If you have a better theoretical understanding of the system, you can build more powerful early warning signals. We don't show this in the paper. There's work showing that you can do this, and I think that's a way forward. Yeah. Okay. But yeah. So I've overshot the target by 20 minutes. Yeah. So I'm, it's a thing I tend to do, especially in lockdown and isolation. You don't have calibrating force. So anyway, I hope some of this has been useful. Maybe check out some of the literature referenced. And just as a last plug, you're probably not seeing it in time if this is being recorded. Oshin, a friend of mine, collaborated defends his PhD today at 6, and you can sort of follow the live stream and check his work out. It's very cool stuff. Okay, so if there are no questions, then I think there might be none because many people have left. I'd wrap it up here. There's a lot of stuff, and yeah.